Wanted to do last time, okay, I gave the formulation or these ideas of first and second class constraints, but I want to see how to apply it concretely for this trivial looking Lagrangian. Namely, I want to see how to quantize this Lagrangian I lambda trace sigma 3 G inverse G dot, where G is in the G is a function of T, is an SU2. I want to quantize this. It is a first order Lagrangian, but something strange is there, okay, because the elements the variables appearing in the Lagrangian are elements of a group, okay, and this is a kind of tip of what we may call as topological terms, namely topological action. Notice that, okay, note, let me, before I even start, okay, this object action is LDT, okay, has no, this is if you look at, is a written purely in terms of differential forms. It involves only differential forms, only differential forms. In fact, one form, right? Yes? LDT I wrote, no? This is typical of topological terms in the quantum field theory. For example, this is the simplest example of the so-called, which is sometimes called as the Wess-Zumino-Witten term. We will come back to the history of this. Wess-Zumino certainly did it, but we also have a stake much before Ed.
But
so
it is not true that if the Lagrangian can be written only in terms of differential form, then it is topological. That's not true.
It is not necessary. That's not a topological Lagrangian.
So that's what I'm saying.
Yeah. So it involves a metric. Here there is no metric in the target space, namely SU. That metric, SU2 metric is not there, right?
No. Why you made this comment that it can be written as a differential form? In many Lagrangians can be written as differential forms.
Purely.
Every Lagrangian is a n form.
That's I should say with no metric. Okay. But anyway, so it is clearly, for example, this is fully diffeomorphism invariant under in T. Okay. So this is fully diffeomorphism invariant if you change coordinates in T. Okay. So this is not canonical. I mean, if you write a point particle Lagrangian, the choice of time doesn't matter. Does matter, no? Here, no. If you change coordinates in T, nothing will happen. Reparameterization invariant in T. Okay. And we will see. So this is one thing. Second, we will see that can be quantized only if lambda is quantized. Okay. We will see the quantum conditions on lambda. Classically nothing, but quantum mechanically this system can be quantized only if you impose quantization conditions on lambda. This is again typical of these topological terms which come in certain terms in the quantum field theory. But this is much more simple, very trivial actually. Now how do I handle this? Okay. This is not trivial. Okay. How to quantize this? So let me give you some technology. Okay. So I should okay. Let me some identities. This sort of how am I going to deal with this, because the elements of the Lagrangian are group elements. Okay. This will happen, for example, if you write conformal field theories where the target space is a group, which is very common, or some coset space. Okay. So I want to get the appropriate identities to do canonical quantization. So, okay, introduce local coordinates for a minute. I won't psi such that G is written as G of psi. Okay. I will not use this psi. These are crutches on the way. I will soon get rid of them and do a global analysis. If you don't do global analysis, you will miss all the fun. Okay. Okay. Then let me do the following. Let T alpha. Okay. Let's say. Let me write be a basis for the Lie algebra of SU2. Okay. It's a basis with, let's say, the Lie brackets T alpha T beta is I times C alpha beta gamma T gamma. So we are discussing semi-simple groups, simple groups, let us say, and you have this standard commutation relations. C's are the structure constants, and I write down this equation. I want to eventually go to express everything in terms of group elements and these operators which act on the left or on the right. Okay. Sorry?
Why are you putting the index on generators in the brackets? In brackets?
This one, alpha, is a basis, no?
Okay.
Alpha is 1, 2, 3.
So just an index for the generators.
Huh?
It is just an index for the generators.
Yeah, there is a basis, no?
Okay.
What I mean is be a basis for the Lie algebra. There are n of them, whatever it is. So consider exponential I epsilon alpha T alpha acting on G of psi. I want to get the signs right. Yeah. Epsilon alpha is small parameters and they act with the group element on G of psi. Okay. This is some G of psi epsilon. Okay. For some psi epsilon with psi of 0 equal to psi, because this is a local epsilon is sufficiently small. Okay.
Which one is it? E to the power I epsilon. Yeah, that's epsilon. That's epsilon. Yes.
I act with this, but this again in the local patch, it is still in the group. Okay. So I can introduce new coordinates. Same, I have the whole coordinate system here, so I call it G of epsilon. Okay. So there is some G of epsilon. I don't know what it is, because I am not going to use this in any explicit way. So now you differentiate. Okay. Implies I differentiate on epsilon alpha and set epsilon alpha 0. So I get I T alpha G of psi. I differentiate on epsilon, so it is d rho of G psi then I get Jacobian of the transformation d psi rho or d epsilon alpha at psi equal to 0. Yeah, d psi rho, sorry, psi rho or d epsilon alpha at epsilon equal to 0. By chain rule.
So what is this? Do you differentiate?
On epsilon.
Ah, okay.
So call this matrix n rho alpha.
That is equal to sign. Equal to sign is not equal. That's it.
So this is, you are finding d rho or g psi times n rho alpha or psi is equal to this. Now you notice that determinant of n is not 0. At this psi I am looking, this is a non-invertible matrix. Why? For if it were not invertible, I can write n rho alpha, okay, some parameters, some eta alpha. So for this equation, if it were 0, it will have a 0 determinant, will imply I times eta alpha T alpha G of psi is 0. From the other side, so I invert by G, I get summation eta alpha T alpha is 0. But the T says a basis is they are linearly independent, so eta alpha is 0. Okay. Okay. Now, why am I doing this? I want to, if you do local analysis, you can immediately go into global situation. Okay. Now, if pi rho are momenta, they are clearly locally, only locally defined, conjugate to say psi rho. So I am writing the Poisson bracket of pi rho with psi alpha is QP is 1, no? So is minus, I think, delta rho alpha. Let me look at what happens. Okay. The Poisson bracket of say pi rho n rho alpha. Let me call this, I think I need a minus sign. Yeah, T alpha. Then I need a minus sign. Okay. Then for the Poisson bracket of T alpha, I want to write the Poisson bracket of T alpha with G of psi. You think of this as a 2 by 2 matrix, and I am taking Poisson bracket with each entry. Okay. So pi rho is this equal to, pi rho is a differential operator, the minus sign, minus minus plus. Okay. So minus minus plus is d rho g psi times n rho alpha, which is equal to, by the identity I have got, it is I T alpha G of psi. See what I have done? So the T alpha is simply acting as an element of the Lie algebra on the left. I didn't need any detail of what is n to do this.
But this is just saying momentum is an infinitesimal generator.
If you do local coordinates, you will get q's and p's, then you will get things like this which have no global meaning, but this is well defined, is a left action of the group on itself, no, this one. The t's here, okay, so what I got is the following, okay. On clearly, okay, T alpha, this I am writing it for G. Okay. Clearly, this Poisson bracket is 0. And I have to prove T alpha T beta. It requires a proof, I will tell you. C alpha beta gamma T gamma. I will check the signs.
What is GIJ? Why are you doing this?
Sorry?
What is GIJ? GIJ.
Gij is a this is a matrix.
Okay, this is C2.
This is element of the group. Okay. This equation I should have written Gij here, Gij here, but it is irrelevant because this is acting only on the argument. Okay. So this is I have proved here what the result is, and you can also say, okay, I will prove this. Okay. Also you can check. Okay. From here, T alpha with G inverse is, I think it is minus I G inverse T alpha. I will check the signs. Yeah. Okay. This is easy because you know the G inverse is identity and T alpha Poisson is a derivation, so you get this. This is slightly more tricky. Of course, you can write everything locally and start doing identities. So, but there is an easier way, star, you compute T alpha T beta with G as G, but when I write G, I mean element by element, Gij, but I won't write the Gij, it's irrelevant. Okay. I use Jacobi identity. Okay. So it is minus T beta G, okay, with T alpha minus G T alpha T beta. No, I want to prove this result, that equation here. This I want to prove this equation. Okay, I not proved it. Star is just to show that I am making that proof. No, just to, because that proof it just requires a small trick. Unless you want to do long calculations, you can get lots of identities on the ends from this equation by doing all kinds of derivations. Okay, then you can get it also from there, but you don't need it because if I look at this, I want to compute this. Okay, this is minus. Okay, this I know, right? I T beta G. Okay, from here T alpha. Okay. Then minus, or it will be simply the antisymmetrization. So is minus. This is minus again. Okay, minus I T alpha G T beta. So let me look at the first term. This is it is equal to minus I T beta. From minus I take it out. Then I have the Poisson bracket here. It is minus I T alpha, right, G. Okay. Then next term obviously is minus alpha beta because of antisymmetry. So it is minus T beta T alpha G. Minus A whole squared is minus T beta T alpha G. Okay, I'll push it through. Maybe I'm making a sign mistake, but it's okay, fine. So this is C alpha beta gamma T gamma on G. Some I should be there. Yeah. Now I go back. So what can I say? So I know that the Poisson bracket of this acts on G like this. So this implies T alpha T beta is C alpha beta gamma T gamma plus some function of psi, function of G, because that is the only thing that will commute when you put it in the Poisson. But the right hand side, but left hand side, okay, is homogeneous in momentum, right? Degree 1 in pi by inspection. Why? This T has 1 pi, this is 1 pi. When I take Poisson bracket, I will knock out 1 pi, but so I am left with 1 pi, right? But this is no pi, so set pi equal to 0 in this equation. Okay, you set pi equal to 0, okay, you get immediately F equal. So this, if I where do you go? Yeah, if I set some pi equal to 0, this is also, this has a pi, so this vanishes, okay. LHS and first, so is first term on RHS, right? This one. So pi is 0, implying F is 0. We are done. So now we have we know how to map. I mean, you can start your calculation with local coordinates, but this tells me immediately how to go to the work with the group and its tangent space directly in terms of the vector fields on its tangent space which generate the group algebra. Okay, and with these vector fields are globally defined. Okay. Okay. So I don't have to worry about Euler angles. In fact, you should, it is a crime to do spin in top with Euler angles, in my opinion. Okay, people should be shot summarily.
I don't understand. In any Lie group, when it is constantly connected to identity, I can work with Lie algebra all of it. If I want, I will experiment it with Lie group.
That's fine. The problem is not that. Okay, when you do canonical formulation,
even there also, what is the problem?
the pi's I cannot. The pi's are the vector fields which are conjugate to local coordinates cannot be globally defined because they are in involution. The Poisson bracket is 0. Okay. Pi Poisson bracket is 0. So the corresponding vector fields commute. Okay. So unless the tangent bundle of the group admits what they call parallelizable or whatever, it is impossible to do that. Impossible that they exist globally because they commute. Okay. Right. So the vector fields, you should be able to find a system of vector fields which globally commute everywhere. They don't exist. For example, for SU2, for I think for most groups, yeah, for any compact group it doesn't exist, because if it did, this is very, if you remember your action angle variables, if it did, you will exponentiate it and find that the group is a torus if it is compact, which you don't want. Okay, right? You know, action angle variables, that's how you do. Okay, right? So you have, if you are dealing with Lie groups, you better change your notation fast. But this methodology gives you control under signs. I mean, when you go from one to the other, you have to be careful about the signs. Okay. So now what do? I want to quantize this. Now until now I only told you, okay, the structure of the cotangent bundle of the group G without ever talking about the Lagrangian. Okay. So we have, okay, described let me write T star G. The cotangent bundle of G. Now I want to now look at L. Now I will show you all problems that Sudipta has been concerned with. So I am looking at this Lagrangian. I want to do canonical condensation. So I will write this as I lambda trace sigma 3, right, G inverse d rho G times epsilon rho dot psi rho dot. But so the momentum conjugate to psi rho, this is the Legendre map. Until now I had known Legendre map. Okay, so I do a Legendre map. So that will give me pi rho. By the standard rules is this is equal to minus I lambda trace sigma 3 d rho G G inverse. Let me call it G. I called it S. Sorry, I think I called it S. So it is G inverse d rho G is weakly 0. Okay, these are my these are constraints. These are primary constraints. Because the momentum is given directly in terms of the, it gives a surface in the T star Q, but these are given in local coordinates. So what do? I multiply this by minus n rho alpha. Okay. Since as it is non-singular, okay, being non-singular, I should have said it earlier. Okay. This mapping, this pi rho to t rho, this change of coordinates is permissible. Okay, I don't lose anything. So I multiply this thing by this object, I get, by my definition, first term is t rho. This is the canonical generator for left translations on the group, minus I lambda trace, okay, sigma 3, then I am multiplying this by minus n rho alpha. Okay, so I think it is I want to get the signs. I hope that eventually it will be okay, I think, times minus n rho alpha I am multiplying, so I get minus I sigma alpha over 2, right, G, and there should be G inverse here. And this is weakly 0. Okay, miraculously all local coordinates have disappeared. Okay. So this is my P rho. So this is saying that T rho minus lambda, okay, from here, okay, trace sigma 3 minus I whole squared is minus lambda trace sigma 3 G inverse sigma alpha over 2 G is weakly 0.
Should be sigma rho, right?
Yeah, sigma, yeah, so should have been here, should have been alpha, because I multiplied by,
Then it should be P
because I multiply by n rho alpha, okay, or this is the same as, but we know that lambda times G sigma 3 G inverse is what I call sigma alpha spin, no, S alpha. You remember that the spin variable was defined like this. So by cyclicity of the trace and then orthogonality, you find say T alpha minus S alpha is weakly 0. Very nice equation. It is saying that the generators of left this is as the Poisson bracket of this with group elements is non-trivial. This is trivial. Okay. This is now I want to see what about secondary constraints. So these are the primary constraints, and the Hamiltonian at this level, this is of first order in the Lagrangian, so Legendre transform will vanish. Okay, so this is only you will get 0 if you make Legendre transform. So it is simply just Lagrange multipliers. So it is simply given by some say V alpha pi alpha. Okay. V alpha Lagrange multipliers. This is Sudhita was asking, give me an example where Hamiltonian is 0. Here it is. Okay. And next 1 or 2 class I will do Chern-Simons, where also similar thing happens. Huh?
In this framework.
Sorry?
Otherwise there are so many examples.
Sorry?
No. Other than that obvious example.
What is obvious example?
Gravity.
Gravity also, that is because of, this is coming because of the same reason as in gravity. It is coming for the same reason, because the action is time diffuse invariant here. Okay. So you cannot have a unique time evolution, because if there were, I can change the, make it diffuse and something is wrong, no? So the Hamiltonian better vanish, and it vanishes. Huh? It is simply existence of time diffuse.
Time evolution is a gauge.
Time evolution is a gauge transformation, but there are many subtleties about what that means in quantum gravity, which are quite non-trivial. In fact, they lead you to physical consequences like ADM energy. How do you define? Okay, that involves some very interesting questions, which I will cover when I do Chern-Simons. Okay, gravity I don't think I will have time, but definitely cover that part. So these are Lagrange multipliers. Now I want to look at you can ask.
No, you said gravity I won't be able to do. Do you have a solution for quantizing gravity, and you don't have
No.
to tell us one of those comments in the
No, the treatment of constraints in gravity. No, I don't have a, if I were, I wouldn't tell you.
It's like a famous in somebody's theorem, conjecture, or something, proof. I don't have space to write.
Forwards.
No, but there are there are several issues. We are going a little bit tangent. First is, how do I understand the constraints in gravity? This is same problem as that occurs in treatment of gauge series. On how do I understand gauge transformations in gauge series, and what is the difference between a charge and a gauge transformation, Gauss law and a charge. Okay, this is highly non-trivial and has serious consequences. For example, in Chern-Simons, when you try to use it for quantum Hall effect, if you don't pay attention to this difference, you will get nothing. Okay, otherwise you will get edge states. Okay, so all the edge states are coming because of this difference. Okay, and ADM energy, similarly, so ADM energy, ADM generators for all the Poincare generators are coming because of this difference. If you don't have it, you cannot define energy, and you cannot define angular momentum or anything in asymptotically flat spacetime. Okay, this has been written already by Hansen-Reje title poem, and people know it. People who are professionals. Huh?
Azteca has written this idea. Whatever you say is simply speaking, which diffeomorphism goes to 0 and which diffeomorphism becomes unity.
But the way you express it as an operator in the Hilbert space or semi-classical Poisson brackets is different. Of course, the professionals know it. Abai knows, of course. Raphael knows. Okay, but
the same idea, no? Is it that
no, yes.
Diffeomorphism, whether they are unity or they are 0?
Yes, but since these are operators, you cannot put this as conditions on the fields of the problem. You have to write it as conditions on the test functions with which you smear them. So that is where the whole trouble starts. Okay, is an operator. What do you mean by operator is 0? What do you mean? What operator is 0? Operator goes to 20. What is the meaning of that statement? There is no meaning. No. So you have to write it in terms of the dual space of test functions. Absolutely essential. I mean, it's not a fussy mathematical point, because if you don't write it, when you try to take brackets, you get absolute nonsense. Okay, you don't know what to do. Then you mess around. Basically, people write Gauss law charge as something at infinity. Okay, you must have seen E dot dl at infinity. Then how do you take Poisson brackets with a field localized at the bulk? Then they do things. You get nonsense very quickly. Okay? Of course, you can always make a masala of nonsense and get an answer. But I will try. This is known. This is not. Is already in Hansen-Reje title poem, and subsequently many people have elaborated on this point. Okay? And Abai certainly, all this treatment of spy group of Abai is contingent on these issues, and Raphael and Friedman in their treatment of diffeomorphism, there is a famous paper, spin half from gravity. There is a famous paper where they show that there are solitonic excitations in pure gravity which are spin half. There is so pure gravity like skyrmion, they discovered that there is spin half states, there are spin half states, but they are solitonic states. Okay? So all these require some very careful attention to this. Okay, then we come here. I want to look at secondary constraints. So I need to know the following. Okay, I want to know what is a Poisson bracket of T alpha with, say, the spin operator Si. I want to know what this is. Okay, so the simplest thing is to look at T alpha with Pauli matrices sigma j Sj. To read out the, so this is this is by definition lambda T alpha times G sigma 3 G inverse, right? Because this thing is this, but I know what T alpha does here is lambda times I sigma alpha over 2, because T alpha acts by this operator with this operator, the commutator with G sigma 3 G inverse. Because this Poisson bracket with this is Poisson bracket with this, that becomes a commutator. Or this is same as I times sigma alpha over 2 times sigma j Sj. I think I got the signs right. So I work, yeah, I think it's correct. I times, I take the bracket here, I over 2, it should be alright, epsilon sigma alpha I times sigma alpha with sigma j, there is no 2 here. So it is I, this is I times epsilon alpha j k s k times something is missing. Epsilon sigma alpha with sigma j is epsilon alpha j k sigma k times s j. So I want to see, I want to peel off the coefficient of sigma k. So this is minus sigma k, right? I squared is minus. Then I have this object here, epsilon alpha j k s j. So this looks, I want to clean it. So k equal to j, k equal to j, j is k, j is k. So I want to look at coefficients. So get T alpha with Sj is minus epsilon alpha, or say plus alpha k Sk. No big surprise. So it just rotates it by Poisson-Braquès. So now I want to look at the, but there is a surprise in that if I take the Poisson bracket of, so I am looking at secondary constraints. So I take P alpha with the Hamiltonian, I want it weakly 0. So that will be, so for that I need, what is P alpha with P beta? Here this is P alpha minus S alpha, P beta minus S beta, no, this is T alpha minus S alpha minus T beta minus S beta. So I take the brackets. The problem is coming, S is commute, but there is a factor 2. So you see the T will go with T, so you will get epsilon alpha beta gamma T gamma. So T acting on this will certainly give back T S gamma. But there is another term here, plus you will get another term here, right? This with this, okay. So that is basically the same thing, minus epsilon alpha beta gamma S gamma. Namely, this acting on this whole lot will give this, okay. But there is another term, namely this and this. So this is not weakly 0, this is weakly equal to minus epsilon alpha beta gamma S gamma. Okay. So what this says is implying P alpha with H equal to 0 implies H is a product of Lagrange multipliers, right? So what this is saying is that this epsilon alpha beta gamma V beta S gamma is 0, is 0. Right? So, but S is a classical function, or V alpha, V is parallel, V alpha is parallel to S alpha. Okay. No secondary constraints. Okay. Now, so with this condition, so let us see what this is. B is parallel to S. Okay. So let us look at what does it mean. Okay. So if I suppose I take the Poisson bracket of, look at the Poisson bracket of V alpha, which is P alpha. Let me take the Poisson bracket, this one with this G, okay, where B is parallel to S. So this is equal to V alpha T alpha with G. Okay. So let me write P alpha here. So this is weakly equal to V alpha P alpha with G, which is T alpha with G, which is I sigma alpha over 2 G. Okay. There is some yeah. So this is parallel. So but B alpha, this is some constant times I over 2 times, this is parallel and you get to S. So this S alpha sigma alpha times G. Yeah. So this is G sigma 3 G dagger, G inverse. So this is constant, okay, some I over 2 times G sigma 3. Right. So it is rotating on the right by sigma 3. Okay. This is our gauge transformation. Okay. So this V dot P is generating gauge transformation G going to G exponential I sigma 3 some theta over 2. You remember at the beginning in the Lagrangian there was this weak invariance. This constraint, this term here is doing exactly that. This term which is left in the Hamiltonian is doing exactly that, and it is saying that the observables must be gauge invariant. Okay. Okay. So let us say, so what are first class and second class? Okay, let me finish this. Okay, so let me do the following. Okay. Observables must have unique time evolution. That is one good way to say it. So they must commute with H, okay. That is, okay, have 0, weakly 0, Poisson bracket with this operator. Okay. So what? So since T alpha P beta is epsilon alpha beta gamma P gamma, it is clear that T alpha are observables. Because this is 0, the P's are 0, right? So this is weakly 0. So this will definitely be okay. Okay, S is not, but the following is, okay, similarly SI, okay, has will have weakly P0 Poisson break. Okay. There are many ways to see it. Okay. Si with the H, okay, which is, if you like, Si minus Pi. So it is Pi plus Pi Pi. I want to get Si as Si minus Pi plus Pi, right? So it is Pi minus. Help me. I want to write S in terms of P and a constraint. P and a, sorry, I am making nonsense. So Pi is Ti minus Si, okay. So Si is Ti minus Pi. Yeah. Right? But this commutes and this, so this is 0. Si are observable. Huh?
P alpha minus S alpha is 0 is a constraint.
T commutes with everything.
No. So one of your primary constraints is T alpha minus S alpha is weakly 0.
T alpha minus S alpha equal to 0 is primary constraint. Yeah.
T alpha are observables doesn't immediately mean S alpha should be observable.
Primary observable should commute with observable need not commute with all constraints, but it has to commute with H for sure, okay, to have a unique evolution. Okay, but I will, in this case we are overdoing it because T is commute with everything. Okay, and likewise you see that SS is what we call spins.
I'm asking you a very simple question, maybe I missed something. If you conclude that T alpha is an observable,
Yeah.
commutes with the Hamiltonian, and the constraint that T alpha is S alpha, the constraints are, doesn't it mean S alpha is an observable?
It also does commute with.
So why a separate calculation?
Oh,
Because it is T alpha comma H. If you put Pi equals 0.
but the SS, yeah, you mean, yeah, I see, that's right.
You don't need a separate
You
calculation.
know, no. Okay, but anyway, what I wanted to say was, okay, so we can simply quantize now the observables. Okay, we can now just quantize observables. Okay, say Ti. Okay, Ti commute with all observables, or all constraints are preserved by the T's. Okay, all constraints are preserved by the T's. Okay, so the existence of, since Ti preserve all constraints, I mean, you can impose, they are completely indifferent to constraints. Okay, they are the constraints are preserved. Their Poisson brackets are unaffected. Okay, by imposition of constraints. You can put the constraints before, after, put Dirac brackets, whatever, nothing will happen, because they commute with everything, commute. But remember, but this equation implies Ti, okay, is equal to Si, which is lambda squared, right? So T's fulfill, so must quantize this equation. Poisson bracket of Ti with Tj is epsilon ijk Tk, and along with T squared equal to lambda squared. That's it. Okay. What I have got? I have got a particle of spin lambda. I mean, that means, so if T hat I is, if T hat is operator for Ti, so I think you just get T hat I, T hat j, the possible is I epsilon ij k T hat k, and you get T hat dot T hat is lambda squared. Yes. So what I did in this way, this one way, what they call frozen phase space. I think this is the language they use. You quotient, you take out all, look at operators which commute with all the constraints. Okay. Then you don't care about the but when you do that, there may be some polynomial relations residual on this set of observables. Then once you do that, you can forget the constraints. Okay. This is called in the people, in the language of people doing especially this gravity and so on, they call it as a frozen phase space. Okay. Peter Bergman used to push this, but there are some awkwardness in this. But I want to show you another way of doing it, and we see that we will get somewhat different results. But anyway, you are getting what does it mean? Okay. This is simply an angular momentum algebra of SU2 with a fixed spin. Okay. So this so it gives particle or spin lambda. So that says, okay, lambda squared is j into j plus 1. Okay, but the awkwardness here is that this lambda is j is not integral or half integral. Normally if you get some topological term, you will think that it is quantized in integral units, but here it is not. Okay, obviously it is not, but there is another way where it will get, another way of approaching the constraint dynamics where it will get quantized in integral units. Okay, so the two answers will coincide for very large j in the class, so called classic large spin case. The two answers will coincide, otherwise they are different. Okay. I want to finish today and ask questions. I will do the second method next time, then briefly treat magnetic monopoles, then go into Chern-Simons where I can bring in issues of gravity, okay, of constraint analysis. But I want to tell you something, okay, that notice the following, note. Similar results will come even if we use another Lagrangian, let me call it I lambda prime trace. Now I will do something different. I will write angular momentum theta 3 r inverse r dot, okay, theta 3 theta I spin 1 angular momentum, then r is in SO3. Do same thing, the calculation, the only thing that will change is the normalization. The theta 3 sigma just somewhere theta 3 squared is 2 or something, okay? But why am I writing it? For suitable lambda prime you can get angular momentum half, that is, okay, that is for suitable lambda prime can get no problem angular momentum half, spinorial angular momentum. they will all describe particles of a fixed spin related to lambda prime, but if you choose lambda prime you will get spin half. So the Lagrangian depends the statement that so tensorial variables in the Lagrangian does not mean one cannot have spin half. When we got into this Skyrmion physics, Skyrm was saying this already, when we entered, then we checked it was happening there also. Then because we had worked with this spin system, we knew that this is nothing great, it will happen all the time, but in textbooks it is asserted that if the Lagrangian is, what does it say, if you put two spin half constituents together you will only get integral constituents. It is wrong, depends on such as, well, in the magnetic monopole case I will show you that that statement is also wrong. You can take spin 0 electron and a spin 0 magnetic monopole, put them together and you get a half integral object, there is no problem. So all these things which one is persuaded to believe without proof are wrong. They are not wrong in some highfalutin fuzzy mathematical way, it's just that's wrong. So we will look at what happens that next time.
So monopole is something link between the internal SU2 and the space-time SU3.
Say you are talking about Ethoff monopoles, there also, but there, yes, but there a more sophisticated this treatment gauge theory has to be taken into account. Yeah.
Space-time, I mean the rotation group and generators are linear combinations of the space-time generators.
Exactly. What happens is that the gauge transformation, you have to add some portion of the SO3 rotation to make something which preserves the boundary conditions. So there are all these test functions, all these things come. So the mechanism is slightly different, but it also happens there. Here the mechanism, there is no mechanism, it is simply fact. There is no big deal here. And magnetic monopole also is the same. But what I want to show you is how complex polarizations also will resolve this quantization. I didn't tell you what is a first class constraint, second class constraint, etc. here. I went too fast to the final answer, but next time I will separate them into first and second class, then apply this Borel-Weilbach, this higher state representation, which is very powerful in fact if you want to do things with Virasoro algebra and so on. If you want diffeomorphism invariance, well, yeah, if you want a diffeomorphism invariance in some fashion in 2 dimensions because of the central term that comes in the Virasoro algebra, you have to treat it in a somewhat different way. So you need a complex polarization. So I will see how that happens in this simple example next time. Then I will say a few words about magnetic monopoles and show this phenomenon, then go into Chern-Simons. Okay.